All right, so today we have the last lecture for machine learning for physicists, and we are going to talk about explainable AI. I wanted to finish with this because, to me at least, is one of the emergent aspects of using machine learning, and one that particularly physicists should be good at and should be able to bring something on. So let me see. Perfect. Okay. So during this course, you've learned a lot of things. You have learned using different types of supervised techniques, also unsupervised techniques, transfer learning, reinforcement learning, and so on. And often we were looking at benchmark data sets like MINST. The accuracy of our techniques was reaching around 90% or higher. And often what happens is when you have your own data set, let's say for particle physics, and you run your machine learning analysis, if you run a neural network, you often get not upset, but disappointed if the accuracy you reach is not above that threshold of 90%. Why? Because those are typical levels of accuracy that a neural network with tweaks and some work done on it can achieve. Also in the course, we learned that machine learning can do amazing things. In particular, you saw how it can beat humans in their highest level strategic tasks, like, for example, playing Go. The machine learning techniques can help speed up difficult computations millions of times, which is very interesting when we think about how we tackle complexity in physics. Sometimes this is with costly and numerical computations, and let's say, the fact that they are so costly also prevents us from actually exploring data sets, exploring simulations, changing parameters so that we can actually understand better what is the true dynamics behind. So to have a tool that allows us to speed up such a huge amounts the computations and our numerical simulations may also open new possibilities, not just to make better simulations, but actually understand what truly is going on behind those simulations, if there is anything to understand there. We also saw yesterday how using machine learning techniques, you can handle symbolic expressions, like in the case of this study, doing integration and solving differential equations using techniques borrowed from natural language processing and context learning. We also discussed how with these techniques one can actually try to solve what it would have looked like impossible inverse problems, in which people shown a data set, or a machine, when it's shown a data set, is able to actually extract the equations that bring this data set to behave that way. Also, we saw an example where, given again a data set, looking at one of the last layers on the hidden layers, we might actually understand that there is some hidden symmetry that produced, or if you want, is behind the dynamics that produce this data set. So lots of stuff, ranging from highly numerical kind of advantages to symbolic on symmetry and very deep advantages that you can find using machine learning techniques. When in the first lecture I told you that machine learning or AI is a very disruptive technology, and that meaning that we don't know yet the extent of applicability and how far it's going to go in the areas that it is already used. This is really because every time you see there is a new technique, a new way of thinking, a new place where the machine learning techniques have been applied to. Now, when it comes to AI, machine learning in particular, we are talking about quite powerful stuff, right? And we are not talking about theoretical studies or something that it really enters into a particular range of knowledge and applicability of, let's say, human knowledge. We are not talking, for example, about basic research. We are actually talking about the algorithms that you in your research develop, maybe focusing on a problem related to particle physics. Through transfer learning or through some tweaks may actually end up being applied directly to societal problems. And it has, of course, good aspects like every new technology and bad aspects, which we already see. With a simple hardware setup, very simple hardware setup power with AI, you can actually track and ID hundreds of people in real time. And which means that, for example, if you have a database of these people, facial recognition, then you can actually follow them, know that they have, for example, broken some law, display it publicly, like, for example, is done in some cities in China. Or you can take huge databases and start scouting, for example, for online posts of users in some platform like Facebook, and start trying to gauge sentiment, cluster individuals based on even just not just post in an online platform, but even just the electricity use they have may allow you to actually cluster them. Even as we probably heard about, just a few clicks can tell you something about the user, for example, something so intimate or some private as their sexual or political orientation. And all this comes from being able to use these machine learning techniques. And the fact that they are very democratic right now, like one thing you probably learn from this course is that most of the things you would like to do in your basic research can be done with a relatively short coding session in which you can then start tweaking and then analyzing, and it might take time to compute, but the things you need to do are already coded somewhere, and you just need to call for them and then use them. This is what's happening not only to you now that you are learning machine learning, but also to everyone that goes online and follows some course or copies some example from some web page, is that they are able to do these things. They probably, people who have less academic education like you, they might have more chances of fooling themselves into overfitting or finding results that are not there, that they are artifacts of the, say, power of expression of neural networks, but they will still be able to do all these things. So it's quite, I don't want to say revolution, but it's probably going to be. Okay, so these machine learning techniques are great, they are powerful, they are showing this every day in the increasing applications that they have. But yes, obviously we cannot just hold AI's hand, close our eyes and jump with it. Because the truth is that we do not understand where this power comes from. We do understand that precisely we made them in a way that they are so expressive that they go beyond our ability to simply code heuristics or do a simple regression. We understand that the power is there, we've given it to the algorithms, but when it comes to taking decisions, we do not understand. They are really, to some extent, black boxes. So from an ethical perspective, we need to make sure the decisions we make based on AI comply with human policies. AI is a tool. It can be very powerful to predict, to find patterns, to find relations, but that doesn't mean that we have to use it, especially if we realize that AI is actually not complying with our ethical views in this world. And from a practical perspective, so this explainable AI is not just because it's related to ethical AI, which is important, but for us, let's say that might not be touching anything too ethical, it's also important to understand the inner workings of your algorithm, at least to some extent. Because at the end, all this power came from us building this particular set of techniques. And then, although AI has gone, for example, let's think on neural networks, and developed into lots of applications and very high precision, the power is still coming from us. So if we poke around with stuff like AI, things that look like black boxes, very powerful, impossible to penetrate and understand what's going on, this will stay as it is. But real breakthroughs, at least in this area, will come from actually poking around that big castle and seeing if it has holes or something is going on with it. So finding what AI does can help us also discover new techniques. So there is no, I would say, we do need to at least make the effort to understand what the algorithm is doing. If nothing else to, because that's our job anyway, to understand things, but mostly because we know that when we start asking hard questions and making relations, human intuition can actually lead to new ways of thinking. Okay, so in summary, to trust AI's decisions and to also help in improving them, we need AI to become more human readable. And that's a concept that is probably quite, like, becoming more in the mainstream, because now we realize, as, let's say, as public, that the applications of AI are surpassing our expectations, in particular when it comes to the impact on, for example, citizen surveillance or obtaining private information. We are now, I would say, most people realize that this is something that we need to at least examine. Okay. So instead of talking in general, because it's all very generic, and you probably say, yeah, wait, fine, but how does it affect the way I'm going to do things? I think it's good to always think in terms of particular cases. At the end of the day, what explainable AI is undefined. There are lots of, again, it's an emergent area in AI, but there are some reviews out there with lots of words of how explainable AI should be, and they talk about fairness, transparency, reproducibility, all these concepts that are so, vague, right? So for us, I think as scientists, we like to first be concrete, and then we can generalize. But first we need to be concrete. So I'm going to give you a couple of concrete problems for you to think on what you will do with the tools that you already have in your pocket. Okay? So let's start with one in particle physics. Let's say, like, a student yesterday was asking how they will do a CNN analysis on their own images for events. And that is like an area in particle physics that is growing and is going to keep growing. Now that we can actually analyze very raw features, and the CNN will take care of trimming out and down all the unnecessary details, and will bring you at the end of this CNN convolutional layers, it will trim down to very abstract and important features, then we can actually handle this. Particle physics, lots of data. In the initial stage is very raw. At the level of the cell zero after the first trigger is like super raw. And that's why there are so many levels of triggering of trigger until you get to the real analysis, where you actually then start transforming all this into quantities that actually are closely related to calculations that a theorist will do. Now we don't have to do all this. And actually going through all these triggers and all these selection processes and then combinations, we might be trimming down important information, like new physics could be there, and we are just not seeing it because we are not looking at it in the right way. So with this mindset in which, for example, in the Large Hadron Collider, we have now new physics, and we are reconsidering whether the approach we have to look for new physics is maybe wrong or too narrow. Then all this thinking about going back to raw features, like even event displays, makes sense. And now you know that this can be done. You can do it with your CNN learning in this course. So let's say that you train a deep neural network, probably containing some convolutional layers, with a huge data set of raw collision images, like this one. And what you're trying to identify is why, let's say, just classification problem of trying to identify whether events are given from new physics or from non-standard model physics. Let's say you train, you tweak, and you train again, and all the stuff that you've been doing during this course, and your algorithm gets super good at it. Like it's super, super good. You get 90-something% accuracy. And you say, wow, that's awesome. But then this super good happens to be not good enough, because for the models or for the new physics you would like to explore, the cross-section, the amount of events you will expect in your detector is just too low. So your 99% accuracy is just not good enough. Okay, even with a lot of luminosity, even with a grace, there is no hope for your model. So you say, well, okay, so that means all my work is useless, and I did the best I could with the current techniques, and I could not reach the level of discovery for the model I was looking for. But then typical physicist, you probably don't give up, because it's very difficult to, to leave the toy alone. So you start thinking on what else could this algorithm do for you. You already tried everything. You changed learning rates, the different optimizers. You changed the architecture. You did lots of stuff in your toolbox of things you could do with a neural network. So then you sit down and say, okay, fine. So I let this neural network, I helped the neural network to learn. I did the best I could in terms of what the network can do. And I gave it the right hyperparameters so it could reach the best learning. But I actually don't know what the network was doing. Meaning I don't know when it looked at an event like this, what it actually did. What did it see there? It started, I don't know, removing places over here, or it clustered stuff. What did it do? And then you realize that you would like to help your algorithm to get better, because you need it. You want this to get at least a tiny bit better so you can reach discovery. And you just can't, because all what you could do within the current framework, you've done. And actually, if you wanted to help a bit more, you just don't understand the way the network thinks. But you still know that to some level, even when it comes to convolutional neural networks, there is something out there that is kind of like you might be able to interpret as a human. Okay, so how do we try to open this black box and see something that helps us then improve our algorithm? So the idea, at least when it comes to CNNs, is that when you start with a CNN, we start with an image. I taken this image for a medical application because it's maybe easier to see. You see this image is an X-ray. If I were a doctor, I would see this X-ray and I would probably know what's going on in the chest of this woman, right? But I'm not, I have no clue. And also the machine that you are teaching is also has no clue at the beginning. So what it's going to do is run through many of these images with some diagnosis, and it's going to learn to identify features in these images that are specific and characteristics of diagnosis of particular illnesses. And with huge data sets, that's what you can do. Now, at the end of the day, you get a diagnosis, that's what you get. A probability for a particular diagnosis, image, probability. But you don't know what happened in between. So one thing that is currently quite very common to do, like for example, I also do it in this kind of analysis, is to look at the last layers or convolutional layers, which did transformations on your image, and you ask to those layers how what regions of the image activated more the neurons that came in the hidden layers. So in the convolutional neural networks, you have input layers. The inputs for the layers are images, transformations of the initial image, but they are images. And what the training does is to assign weights to regions of the image. The higher the weight, the more is activating the neuron. So the more importance this region has. So a typical thing to do then with CNNs is to try to plot a saliency map, see what areas and what regions are more salient, to visualize what the AI is actually doing. In this case, this is the saliency map with the lighter colors, meaning the more activated the region is. If you overlay these two, you get this kind of plot, where essentially you see that, for example, there is light color over here, which corresponds to some feature in this chest. Again, I have no clue about medicine and I don't want to know about medicine, but there are stuff over here that apparently the network consider important. Now you can do that in your own particle physics problem. You can, if you are feeding images, probability distributions, or images of raw events, or whatever you're doing, you can then go. Yeah. Any questions? No. You can then go back to your analysis and actually understand image by image what kind of features the AI is identifying as important and what kind of things is trimming out because this is not important, right? For the case of the chest image, even if you're not a doctor like me, you still understand that probably this region is not important and there is something going on in the lungs, and if there is a cluster of something white, that's probably something. And that's obviously what the AI is doing too, to a much higher position than us and to a similar position than an actual radiologist. So in the context of particle physics, I would say this area is emerging, but there are groups working on explainable AI, and they call it like this, some groups, and some others, they are just doing what you will do, which is you reach a level of accuracy with your technique and using machine learning, and you actually need to understand what's going on, either because you want to improve your algorithm or because you need to justify to your collaboration that you are using a neural network and you are not able to explain such an, let's say, an increase in precision, or because you want to understand again some level of systematic error you are making by using a new and mostly unknown technique. So these kind of techniques, as far as I can see in the area of experimental particle physics, they are starting now. There is, I would say, more in the data quality area. detect or monitor it, because all this can be done online and so on. And they're certainly widely used in machine learning in medical applications. Okay. So this was about medicine. I told you that in physics, this is emerging, so there are not so many examples yet. But if we come back to this new physics problem, again, you are this person doing an analysis, searching for very difficult to find particles, and you realize that your algorithm is super great at actually distinguishing BSM or new physics from the standard model, but it's not good enough, and you want to give another edge. So by doing this explainable AI analysis on the results of your algorithm, for example, by looking at the saliency maps in what it's doing on the event, you may realize that, for example, I'm just here imagining, that there are some typical salient features in the images it identifies as new phenomena. For example, by looking at them, you as a human, you may realize that this particular set of configurations could be enhanced by changing the selection trigger at your analysis level. Let's say you might have used a two-jet trigger or a MET trigger, and actually realize that in this kind of setup, and with what the neural network is telling you, which is focusing on particular areas of the image or the event, you realize that actually maybe having just a soft lepton and some lower MET would help as well. And with those lower level triggers, or sorry, less softer triggers, you may actually be able to accept a lot more signal and then redo your analysis. And since these triggers are usually, let's say, on PT, on energy, they tend to be quite at least polynomial or even exponential. So you can change trigger or lower the trigger. Yeah, the increase in data in signal acceptance can be huge, right? Or even you might realize that what the neural network was focusing on were topologies that are not currently captured by the existing trigger menu. And you might be able to say, well, if you want to find this kind of new physics, you probably need to add this particular trigger to the menu. And maybe after all this work, you realize that we're running with an improved trigger, so collecting more data and doing a different analysis, you may go from hopeless to actually having some hope of finding new physics. Okay, any questions?
Yes, which are the images that we use like input in these examples?
So there are lots of stuff of different options out there in the literature. And again, I'm talking about an area that started like 2 years ago. So I'm not talking about hundreds of papers. But sometimes the analyses are made with raw stuff like this. More often than not, it's not such a mess. What they take is an image. Let me say. So imagine a projection on the transverse. Are you an expert, particle physicist?
Yes, I'm in the master.
Great. Okay, so now you know there is a transverse plane, and when we talk about transverse momentum, the angles and so on, is in this transverse plane of the collision, and there you have a distance from the center of on the action point all the way to the muon chambers, right? And a particle, when it's produced in this transverse plane, it can go enter into the inner tracker. Then maybe if it's a hadron, it will mostly be stopped at the hadron calorimeter. If it's an electron, photon, it will be stopped over there, leaving some deposition of energy and some track. Or if it's a muon or a long-lived particle, it might just go even further and arrive to the muon chambers. And in many different ways, you cannot capture this. So imagine that you take a snapshot of one event where what you have is precisely that. you create, let's say, a couple of Higgses. These Higgses immediately decay into 2 bit jets, and the other decays into 4 leptons. So imagine in your head what kind of image you can draw of this. You can draw a distance and trajectory for the bit jets with the different tracks that is going to live. And you can then depict the amount of energy that the bit jet had as maybe a color coding. Then you can, these leptons that the other Higgs produce, there could be 2 muons and 2 electrons. So you will see another 2 tracks of electrons that are stopped in the electromagnetic calorimeter, or 2 tracks of muons that appear and arrive to the muon chambers. And that's the picture of your event. So imagine you produce many of these pictures with double Higgs production for the standard model and double Higgs production for new physics, like a composite Higgs or a new heavy scalar from supersymmetry. And then you train on those images to actually identify what is typically a standard model and what is typically BSM. This is one example of what you could do. But you could think on any transformation of these images and other ways of expressing this information. Okay?
Okay, thank you.
Okay. And also, instead of event by event, you might also plot possibilities of probability distributions in a two-dimensional space of the, for example, kinematic features. That's something I've done as well with machine learning. So there are lots of different options when it comes to that. All right, so that's the particle physics example. Any other question on it? The idea here is that in anything that has to do with CNNs, the technique to follow, if you want to understand what's happening, is probably some version of the saliency maps. GradCam is a very common one, but there are many others. Okay. All right. So it is a practical. What I showed you before is a practical problem. You are using AI to improve your way of finding new physics. It works very well as it should, but it doesn't arrive to the place you wanted. So you need to understand a little bit what's going on to help a bit more this kind of analysis. And that's why you need to explain your AI. You need the AI to tell to you what it's doing so that you can actually help. And that's a help that you could do is to change, for example, the trigger. But of course, most of the interest in explaining AI comes from, let's say, the general public. Is, for example, a fact that when we take decisions based on AI being a black box at the beginning, we don't know whether those decisions are actually ethical. And ethics, maybe for us, is not something that we have in mind all the time because we do basic research. So I thought of giving you a particular example so that you can put yourself in the shoes of somebody who needs to handle these ethical aspects of AI. So let's say that you are not a physicist, or were, but not any longer, and you are working in a company in the insurance sector. And your task, maybe a data scientist that has been hired by this company, is to assess the level of risk of customers when they apply, so you can fix a premium that is fair, meaning fair for the company. There will be customers that are more risky, in quote unquote, and then their premium should be higher. Otherwise, if the company wouldn't make money, right, and couldn't offer that service. So you as the data scientist, you are told, okay, here there is a huge database, historical database. We have a huge amount of customers where when they apply, they fill some form that gave these customer descriptors. We know what happened with them. We have a historical record of what this particular customer has done and how many claims it has done and for what amount, right? So your X is the customer descriptors and your Y, the result of giving them a premium or giving them an insurance. Now X, you probably filled some of these forms in the past, and X has lots of information about you. It has the name, the date of birth, the address, sometimes the level of studies, the gender, sorry, I wrote this again. So the medical history details, especially if it's an insurance that is a life insurance or medical insurance. And even in some cases, in the case of banks, for example, this one, that they have done this kind of data mining on customers, also based on their Facebook history, friends, and so on. So there's a lot of info out there, not only the information you give, but also the information about you that can be obtained, again, with the stroke of a finger. But okay, you just take in your database, this is your job, you're trying to find a good descriptor of, given a customer characteristics, what kind of premium we should give, on whether we can actually give them or offer them an insurance or not. So you run a machine learning algorithm because at the end of the day is a problem with many, many features in which no clear trend is seen anyway. So something subtle. It's also big data, many customers, many possibilities for the history of claims. So the most rational thing to do is to run a machine learning algorithm. And as it will happen, if you do your job well, your algorithm will become very good, extremely good at predicting why. So if you give a new customer with their data, you will predict very, very accurately what their future claims are going to be. So from your standpoint, as a person hired by this company, you can compute the most fair premium for your company as well as for the customer. You can maybe offer an insurance to a customer that maybe another company wouldn't give. Let's say, imagine that there are, in the medical sector at least, many companies that will not give offer medical insurance to some customers that have a pre-existing conditions or whose parents had a heart attack in early age and so on. They are like hierarchical thresholds that then make many medical insurance companies to reject and refuse applications. But maybe your algorithm is actually better. It takes into account that although the parents had or they were pre-existing conditions, that kind of condition has a very good prognosis, or their everyday habits are really good, so you're probably not going to run into the same problems as health problems your parents had, and so on. So your model, from your standpoint, is actually better, quote unquote, because it can allow more people get medical insurance. Okay, because you are so much better, so much more precise. But I guess the main difference is that for you, but you gave this task to a machine and it gave you very good results, whereas other companies may just have a set of criteria, a decision tree you want, with thresholds, and the criteria is laid out, it's very clear. You know when you don't get an insurance, whereas in your machine learning case, you just know that you let pass more people, so it seems more fair, but you actually don't have an understanding of why this is happening. You just know that you are getting better at the task you were given. Predict the claims that this customer is going to do. But you are a person, right? So you are a data scientist and a scientific mind, and probably you want to do the right thing and don't want to just release the power of decision. So you start getting itchy, thinking that you allow that black box take decisions which affect people's life. For example, the fact that some customers will not be accepted to be offered an insurance, or a better maybe motivator is that you get an audit, and then you have to explain why you took these decisions. Okay, so imagine you are that guy or that girl, right? Somebody who is trying to do their best They're meant using machine learning techniques because they are more powerful than the ones that can handle all these data sets and take the best decisions. At least that's what you think. And then you realize that actually something is pushing you to try to understand what's going on. So, to you guys, to the students, can somebody tell me, I don't know, what would you do if you were this guy or gal? Yeah. You have the data set, you have your model is running, it's great. Whenever you introduce a new customer and you examine a new data set, you see it generalizes super well, really predicting super well what's going on. But now you need to understand what happened. So anybody has any ideas of what they will do? No, I will ask questions. Let's say Jesus Guerrero, since I see you. Are you there, Jesus?
Yes, I'm here.
So imagine you are this guy. What will you do?
I didn't understand very well the question here.
Okay, let me pause it again. You have a data set that tells you customer characteristics and their claims, how much money they ask the insurance company to give them. And you create a neural network, for example, to be able to predict, given a customer, what kind of typical claim they are going to make. And the neural network works very well. It's robust. It generalizes. Your job as a data scientist is done. Now my question is, now you want to understand what's going on? You want to actually understand what's happening? What would you do?
Maybe I can use a customer to see what is the response of the neural network, to see if there are some bias or something like that.
Okay, so you will look at a few customers. So you will see locally that I take this customer, it gives this result, and try to understand what's going on. No?
Yep.
Any other? But you are a scientist. You know more than just input output. What else would you do? Because we are talking about huge data set, right? I guess you will start plotting things, no?
Yeah, first.
Yeah. First thing we will do is plot stuff. We will do data visualization, looking at the characteristics and looking at what kind of correlation it has with our predictor. Any other thing you will do? No? All right. If you can stop Jesus, no worries. Okay, so what you will do is follow the steps that you have followed so far. You have done a supervised learning. A very important thing before doing any kind of analysis is, of course, do data visualization. So start plotting stuff and try to see if there is any trends you already can observe. But then what you will do, given that you already have a pre-existing machine learning algorithm that works very well, is to post hoc understand the process. And there is no like predefined way of doing that. Otherwise, there will not be this lecture. I will just tell you, follow this procedure and we are done. This is like a try and test way. And the procedures for bringing AI to be explainable are not set yet in stone. These are decisions that are being made now. So one of the things you could do is to run the same data set over a boosted decision tree. So to try to actually see what your algorithm is doing as compared with these other companies who already use this kind of heuristic approach of just giving thresholds. If you have pre-existing conditions, no, if you and so on. And you see what a boosted decision tree. in boosted decision trees, and that's something that you have an example in the notebook of PCA and clustering. You can also do feature importance. So after running the boosted decision tree, as I told you, you can also ask which features are more important, which ones appear first, and which ones appear more often. So that will start telling you that features are particularly important. Now, you might also do something simple, which is what I will do without using anything else after data visualization, would be to rerun my algorithm, dropping features. All these things, going from a neural network to a boosted decision tree or dropping features, are going to reduce the precision. The accuracy is going to drop for sure. But we want to get is a feeling of how much. You may want to run PCA, so just looking at X and see whether there is any dimensionality reduction that you could do, telling you then that there is some clustering that you could do, and then going and inspecting this clustering, these clusters, and try to understand whether there are features, which is what I think was behind Jesus' thinking. He will go and look at the specific customers to see whether there was a systematic lack of precision when it came to those types of customers. Okay? And let's say that after all this digging, you would realize that the main predictor for why the being accepted or refused an application, after doing this post hoc digging, you realize there is some combination of the customer's address, let's say the postal code, the postcode, and the name, which at least in the UK might be related and can be quite correlated with religion, or even you realize that there is some clustering around level of studies, age, and gender, or some other combination of these customers, which again seems to be correlated with political orientation. And also you realize that predictions for minorities, those groups of people that are less represented in the data set, have the accuracy you arrive on predictions for those are substantially lower than the rest. And this, by the way, is something very typical that is going to happen, not just in real life applications, but in physics. If you have an unbalanced data set where you have a group that you want to predict over that is much smaller than other groups, your machine learning is going to try to do is to generalize, and that means that it's going to give much less accuracy to the smaller component of your data set. And to cure that, this is a problem called unbalanced data set. There are a set of techniques. This is very typical in physics when you are, for example, looking for anomalies, for example, the breakdown of your system, something that is unusual, for which you don't have a lot of statistics, but you still need to focus on. And same could happen to this guy. It starts looking at his predictions, and he realizes that for minorities, since they are less present in the data set, when it comes to predict their outcomes, it's much worse. So he thought he had a 90-something% accuracy, but he had that accuracy in the whole data. Whereas for this particular group that is very defined and from the societal point of view, the accuracy is much lower. So after you're digging out and trying to understand to yourself or maybe to an auditor what you've done and why your decisions are what they are, you realize that your company is making discriminatory decisions based on legally protected characteristics like religion or political orientation of the individuals, and hence is breaking the law. Okay? So this is going to happen in the sense that whenever you use an algorithm that comes from machine learning into a data set that has to do with people, and you want to take decisions based on them, you are not going to be able to just blindly go ahead with it. You will have to do some digging. The procedure, as I said, is not set. It will be up to you to try to understand in your problem what of these techniques of the post-hoc understanding are useful. And there is no, as far as I can see, clear ways of doing this in a consistent manner for all kinds of problems, even just when it comes to ethics. Here I would just a reference to something called DICE. Of course, there are groups of people who are trying to define good procedures to make sure that decisions are made in an ethical way. But my impression is this is not yet clear. DICE is particularly interesting to me because it tries to do something unusual, something that is not reflected in this. All right, so again, there are some reviews on Explainable AI. This is a particularly nice one. It's quite new and it's also from many Spanish people, which is nice to see that they are on top of this kind of stuff. To me, it's blah blah. It's essentially recapping on what's going on, what kind of techniques are out there, and so on. But it does lots of graphs like this that are very useful when you want to express ideas. But in the context of this insurance guide, what the techniques we have been talking about are reflected here. So you have a black box model of X goes to Y, and you don't understand what's going on. So you have many options. Some of them are here. You can run these boosted decision trees and see the feature relevance so that you see that a feature is very important and maybe this feature is actually sensitive. Or do what Jesus was saying, looking for local explanations. So you take particular customers and you see what happens to them. Or even the customers may realize that they are being treated unfairly, and then you use that local explanations to improve your algorithm. You could also do some kind of clustering analysis like this one, and then realize that there are clusters, and then examine whether the accuracy and the treatment of your algorithm is more or less equal among these clusters. Or you can take your model, and as I say, the first thing I will do is to start dropping features or changing features, combining them, and see what effect it has on the accuracy. So you will simplify your model. You will also look for text explanations, meaning if you do a boosted decision tree, for example, or a decision tree, you will find that there are thresholds in some of the variables. And for example, it could be in pre-existing conditions. Or again, following the lines of what Jesus said, you could find explanations by example. So by realizing customers, for example, that were rejected before, they pass because there is something that the algorithm is taking into account and trying to understand what. So there are many different ways in which, if you really want to understand this black box, you can go about it. There is no one, there is many. And for your problem, there might be one that is most suitable and others that are useless. Okay, something to keep in mind. So in today's notebook, this is what you are going to do. You are going to try out some of these different ways of things using what you already know, using neural networks, using clustering, PCAs, using decision trees, and so on. We are going to use the following data set. I thought that it would be good to use a data set where there is some at least motivation to think about ethical issues. And what that is very common is to use this US census of citizens, where they collected many characteristics of citizens, and then they recorded whether their city was above or below a given threshold of $50,000. That's a good amount in the US. Let's say so, like a postdoc will get. Okay, so of course there are not many people in the US that get this salary. The amount of people above this are much smaller than below. And the kind of problem you are trying to set is a binary logistic regression. Given these characteristics, is my salary going to be above or below this particular threshold? What I show you in the notebook is to run a shallow neural network, just has 1 or 2 hidden layers. And I get, with some tweaking that I had to do, 85% accuracy, which in this data set is the best state of the art. There's nothing out there that is better than that. So I want you to then look at what I've done, think about the data set, and then realize that you have obtained a very high accuracy. Or 85% is not bad for this kind of data sets. And still, you don't know whether the decision to assign you to, or to think that your salary is high or low, what it's based on. And it could be this decision, your salary is high or is low, this predictor determines whether you get, let's say, an insurance, or you get a premium, or you get something of some importance to you. So it's important for you to know whether this prediction is based on stuff that should not be taken into account, or that is sensitive, that is very private and personal. Okay. We will have no 1230 catch up. This is a long notebook in the sense that I've given it to you already as this guy in the insurance example. You go through the data set, you do some feature engineering, I've done that. Remove some stuff that was spurious to make sure that all the entries were correct and so on. And then I run a neural network and it looks great. So I can predict very well. But now your task as a student start is you are going to do explainable AI on this data set. You are going to try all these different techniques on the data set and try to arrive to some conclusions. And in particular, one of the things that will happen is that your data set is unbalanced. So I'm asking you to think or to check out what kind of techniques are done in terms of unbalanced data sets. Because this is something that you as physicists are going to probably encounter at some point. When you are looking for new stuff or for breakdowns of your systems, those instances are not going to be equally balanced with the normal instances. So dealing with unbalanced data sets like these ones is also important. Okay, so keep an eye on that. So we have no catch up. Also don't want you to be stressed trying to say something at 12:30. There is no point. You already have all the techniques you need to do this notebook. You learned lots of things before that you can simply copy, paste, and apply to your particular, to this particular problem. So I want you to do that and to explore and have fun. Any questions you have, again, send them via Slack or directly by email. But again, by Slack, probably somebody else is having the same issue and maybe he or she solved it. So it's probably more efficient. All right, so that's all for this course. Unless you have any questions.
Veronica, I'm trying to click on the link for the notebook, but it says I need permission.
Ah, really? I did this mistake again. Let me just upload the notebook again. So probably I just copied the address when what I should do is to actually share. Let me do that, and in a second you will have the new PDF with the correct. Thank you, Roberto. Yeah, I did this mistake already. Yeah. Any other question? Nope. Okay. So I hope you learned a lot during this course, so at least you got the idea of the kind of things you can do, and you take today as an opportunity to wrap up some of these techniques, supervised and unsupervised, on a specific data set with some ethical considerations. Okay? And then you are able to actually apply all this to some of your research, which I think is likely you are able to do. All right, so nice teaching you. See you.
Thank you.